Now we're going to talk about constant pressure calorimetry. So the bomb calorimeter was constant volume. It's a sealed container. The volume can't change. The pressure might change. Constant pressure calorimetry is going to be open to the atmosphere, and the volume changes are going to be negligible, so we don't need to worry about them. But this can be used to measure the heat of reaction. So this is a very basic constant pressure calorimeter known as a coffee cup calorimeter. It's got two styrofoam coffee cups nested inside of each other, just for a little better insulation than a single cup. It's got a lid here that's just sitting loosely on top. In the picture, this one's made out of cork. We're going to do this in lab, and our lids are made out of cardboard that is older than you are. These pieces of cardboard have been used as calorimeter lids for like 40 years, right? So be careful with them. They're actually really, really sturdy. So you have your chemical reaction occurring in here. You have a thermometer so that you can monitor the temperature, and it needs to be stirred so the reaction occurs and the heat, gets all over the place. So here we have Q solution and Q for the reaction. So the solution is the aqueous part that the reaction is occurring in, right? The water. That's what we can measure the temperature of. So we can measure the heat absorbed by the solution if we know its mass, its specific heat capacity, and we measure the change in temperature. All of that's very doable. That heat that the solution gained came from the reaction, right? So Q reaction is the same number but opposite in sign. If Q reaction is negative, then Q solution is positive. Q reaction is the same as Q at constant pressure, which is the heat of reaction. And normally those are specified per mole. So to do that, you're going to look at the amount of stuff that reacted in moles, and you're going to take the kilojoules and divide by the number of moles. Yes?
Can we say that the Q solution is the Q surrounding?
Essentially, yes.
Oh.
Yeah, Q solution would be the surroundings, and the reaction would be the system. Now, technically, the surroundings would include the cups themselves and outside the cups. But we're hoping that not much heat is escaping from the cups. Okay? Actually, a tiny bit does. And you can calculate that, and we will in lab. But that's the basic idea. Okay. The addition of hydrochloric acid to a silver nitrate solution precipitates silver chloride according to this reaction. When 50 milliliters of 0.1 molar silver nitrate is combined with 50 milliliters of 0.1 molar HCl in a coffee cup calorimeter, the temperature changes from 23.4 degrees Celsius to 24.21 degrees Celsius. Calculate the heat of reaction for the reaction as written. Use 1 gram per milliliter as the density of the solution and specific heat capacity of 4.18 joules per gram degree Celsius. So what's happening here is we have this reaction that's occurring between the silver nitrate and the hydrochloric acid. And that is going to, we can look at the solution changed from 23 to 24. The solution got warmer, so is the reaction giving off heat or absorbing heat? I know, right? It makes your head spin. The water got warm. That means heat came from the reaction, right? So Q for the reaction is negative, the heat went out, and Q for the solution is positive. But they're the same number, so you just have to stick a negative sign in there and then they're equal. So we can calculate Q solution. Q for the solution equals the mass of the solution times the specific heat capacity of the solution times the change in temperature for the solution. So we were given initial and final temperatures. We can calculate the delta T. We were given the heat capacity, the specific heat capacity. They didn't give us the mass, but we have enough information that we can figure it out. I keep accidentally pausing the lecture recording, so my apologies to people in the world of YouTube. Sorry. We've got 50 milliliters of this solution and 50 milliliters of the other solution. What's our total volume? 100 milliliters. Right, so we have 100 milliliters of solution, and we're told to use a density of 1, so we could calculate the mass from that, right? So the mass of the solution is going to equal the 50.0 milliliters plus 50.0 milliliters times 1.00 gram per milliliter. So that's going to be 100 grams. Three sig figs. I'm going to do delta T up here. There's just not much room here. Final, 24.21 minus initial, 23.40. 0.81. So Q for the solution will be the 100 grams and the specific heat capacity, 4.18 joules per gram degrees Celsius, and the change in temperature. So 100 times 4.18 times 0.81, 338.58 joules. How many sig figs? 2, only 2. When we take these nice 4 sig fig numbers and subtract them, we lose some sig figs because the difference is not very large. So the sign there makes sense because the solution was getting warmer, it was absorbing heat. So Q for the solution, from its point of view, it's gaining heat. But that means that the reaction was losing heat, right? So Q for the reaction is equal to -1 times Q for the solution, which is -338.58 joules. So we found Q for the reaction, but they want delta H for the reaction as written. So delta H up here would be the amount of energy that's released for how many moles of silver nitrate? 1. How many moles of HCl? 1. How many moles of those do we have in this reaction, in the coffee cup? Well, we have a volume here, and we have a molarity. Let's do this in a different color. So 50 milliliters, 50.0 milli times 10 to the minus 3 liters times 0.100 moles per liter I don't know what I did. Syntax error. Leave me alone. 50 times 10 to the minus 3 times 0.1. 0.005 moles. So the volume converted to liters times the molarity gives us the moles of silver nitrate. How many moles of HCl are there? The volume's the same and the concentration is the same. So 50 times 0.1 with the correct units is the same, right? So we have an equal number of moles. So we actually reacted 0.005 moles, and we want to know how many joules or kilojoules per 1 mole. So the heat of reaction is going to be the negative 338.58 joules divided by the number of moles that we actually had. I didn't write that very well because I was out of space. The 50 had 2 zeros after it. It had 3 sig figs, and this had 3 sig figs. The way I wrote it there was only 1, so it's actually like this, moles. Negative 338.58 divided by 0.005. Negative 67716 joules per mole. Well, that would probably be best expressed in kilojoules, which would be, and we've got 2 sig figs, so negative 68 kilojoules for every mole of reactant. Yeah.
So that mole that we got from one of them, we don't have to add up with the other one?
No. You don't add the other one because really what you have to figure out is what's the limiting reactant, because that's how much is actually reacting. Anything extra is just going to be sitting there, right? So in this case, we had equal amounts of those, and the mole ratio in the equation is 1:1, so we had just enough of each, which doesn't happen very often.
So that is the mole of the result?
Yeah, so this is the moles of this. It is also the moles of that, but we want the energy per 1 mole of that, or per 1 mole of this. So I'm not going to add the 1 and 1 and get 2. I'm not going to add the 0.005. Okay. Any other questions? So this is conceptual. The same reaction with exactly the same amount of reactant is conducted in a bomb calorimeter and in a coffee cup calorimeter. In one of the calorimeters, Q reaction is negative 12.5 kilojoules, and the other is negative 11.8. Which value was obtained in the bomb calorimeter? Assume that the reaction has a positive delta V in the coffee cup calorimeter. You know what? I don't like that question. I think it's too picky. We're not going to do it.